Go live.
Okay.
We can say something again.
Okay. Hello. Hi. Good morning.
Okay, there is some like noise with your voice. Is it?
There is some noise. Okay. As in, not echo, right? Just noise. Maybe it's because of the fan.
Okay.
Okay.
It is okay now. It is okay. Right now, the way you are speaking, it is okay. Okay.
It is okay, right? Okay.
Yeah. Okay.
Then, are we live in on YouTube?
Okay, let me check.
It's fine. I think you can start. It is already live.
It is live, right? So, okay, then. Okay, then I'll start.
Yes, we are live.
Okay, thank you. So, yeah, let's start today's session. So, first of all, good morning to everyone who is watching us today. And I would like to first give a very brief introduction about our speaker here today. So, Dr. Vikram C. Mathad, sir, he is working as a research scientist at Zapper Media Labs in Bangalore. He received his PhD degree in electronics and electrical engineering from the Indian Institute of Technology, Guwahati, in 2019. His thesis work was focused on the automatic detection of misarticulated consonants. He was working as a postdoctoral researcher in the Department of Speech and Hearing Science in Arizona State University in the US, where his work involved the development of speech-based objective assessment methods for cleft lip and palate, dysarthria, and Alzheimer's disorders. He also worked for the funded project sponsored by the Ministry of Human Resource and Development, the Department of Biotechnology in India, and the National Institute of Health in USA. His research interests include speech signal processing, biomedical signal processing, and machine learning. So we are very fortunate today to have Dr. Vikram sir. And without any further ado, I would like to hand over the session to him. Thank you, sir.
Thank you very much for this opportunity. So today talk is about machine learning for clinical speech processing. So overview of talk is say brief introduction for clinical speech processing and why this clinically speech is more significant. And next we will go for the one of the case study, that is using machine learning approach, how we can develop an automated system for the assessment of hypernasality. Next, I'll be explaining the practical consideration for this clinical speech research work. So, in an introduction, we know that speech carries linguistic and paralinguistic and most of the time non-linguistic information also. Non-linguistic means like age and gender and emotion. Linguistic means we can easily understand what is the language the person is speaking. Paralinguistic means it's not directly related to language, but like any the expressions we can see whether the person is asking question or is explaining something. So these are the different information we can get it from the speech signal. Coming to the production of speech, we all know that speech is produced from the vibrating vocal folds. For the vocal fold, the source of energy is delivered from the lungs. Further, the vibrating vocal folds convert the air into a periodical puff of acoustic energy. Further, it is passed through the vocal tract system, which considering of oral tract and nasal tract. Here, different resonant frequencies are added to the vocal fold vibration. And finally, through lips or from nose, we can emit the acoustic energy. So this is the overview of the speech production system. Say this is an schematic view. Say suppose we have two different tracks here. One is oral tract and another one is the nasal tract. Say the sound emitted from nasal are called as nasals, like ma and are the different sounds. Most of the sounds, there are only few nasal sounds are there. but lot of them are like oral sounds, like pa, ta, sa. These sounds are the oral sounds. These are the different application of speech processing. Everyone or most of us knows like many applications, like automatic speech recognition is the most common, like well-known application of the speech processing. Then text-to-speech synthesis, then speaker diarization, emotion detection. But apart from this, we have one more area, that is clinical speech processing. So suppose using speech, we can able to judge whether the person's mood, that means whether he is happy or whether he is in angry mood. Apart from that, we can easily say there are some easily say some clinical symptoms, like whether the person is having cold, either the person is having some mouth ulcer, depression, then fatigue, emotion, fever, sleepiness. All these things, these are related to our physiological or our physical, related to our mental or physical health. But however, they are reflected in the speech signal. So apart from that, like we can like many like clinical aspects we can able to judge from the speech signal. So suppose just coming to the vocal fold, these are the pair of vocal folds which are like major organ in the speech production. Say the vocal folds vibrates in periodic way. Say suppose right now the vocal folds are closed here. Later they get open and finally they get closed. Like this, rhythmically vocal folds vibrate, and using this we can able to produce the speech. Say these are the normal vocal fold structure. If we have some mass or something like some clinical condition is appearing on our vocal fold, then our speech quality or speech characteristic will get changed. So suppose these are the different symptoms I shown here. One is cyst or the nodule and GERD reflex. GERD reflex means over acidic reflection from our stomach will damages our vocal fold, and it causes the GERD reflex. Then this is an edema, that is some kind of liquid formation on our vocal fold. Whenever we have the such sound, such vocal folds, our the produced speech quality will be differs. Just I will play one sample. Say this is the normal. And one more sample, that is just I will play the nodule sample.
Vikram, you unplug your microphone.
Yeah, I unplugged it.
Okay.
Okay. Sorry. Say just we noticed that there is some difference in the two different speech samples. Say one more example is the vocal fold paralysis. Say here one vocal fold is vibrating, another is get paralyzed here. Here also we can notice some change in the speech signal. Say this is one more disorder, that is Cleft, Flippant, Palate. Here we just notice that the palate is an organ where our tongue goes and touches when we produce the speech signal. But in these cases, the palate is entirely like damaged here. It is a kind of some like the roof of, just we can imagine that this is the roof of our mouth. Say this is got cutted here. So in this Cleft, lip and palate also the speech characteristics will get changes. Just I will play one example here. Say this is in Kannada language. Are you able to hear this sound?
Yes.
Okay, thank you. Say this is the normal speech sound. Say just I'll play the another example now. Say just we noticed that when the palate is completely damaged here, user speech signal characteristics, like they have a lot of deviation from the normal production. Next, one more disorder is, say suppose hearing impairment we have. Here also, like we learn the speech production through hearing. Say since our hearing organ, that is hearing organ is damaged, then we can expect some deviation in the speech quality. Another one is, just now we seen that cleft palate and vocal fold disorders. Another important disorder is motor speech disorders. We know that the coordination between different organs in our speech production is happening because of our nervous system. So our nervous system sends some impulses or signal. Due to that, our vocal folds or vocal tract, different organs get some movement, and we can able to produce the speech signal. So suppose if something happens in the nervous system, say some damage happens in the nervous system, that will directly affect the speech signal. Say different disorders we can see that, like stroke or Parkinson disease or Huntington disease or cerebral palsy. In these different disorders, the speech quality is completely deviated from the normal signal. Say one more disorder, it's not directly related to the speech production system, but it is related to the memory, that means our memory system. Say it is like cognitive impairment disorders are there, say Alzheimer's disease, dementia, then these kind of cognitive impairment disorders are related to the memory impairment. However, we can easily detect from the speech signal. So suppose for some person who is having this Alzheimer's disease, if we tell them to explain this picture, just imagine that I put here the some text of the speech produced by the person with some dementia or Alzheimer's disease. We can notice that there are a lot of filler words are there. In between, he laughs or he memorizes and he says lot of filler words like then some in between and coughing. So these are the different symptoms which says that the possibility of the cognitive impairment. So now just we analyzed that using speech signal we can able to detect the different physiological aspect of our brain or the speech production system. That's why this speech has an importance in the diagnosing some of the disorders related to speech production system as well as our nervous system. Say how the speech got assessed in clinic. Say clinically, like speech language pathologist is an important person who can interact with the neurologist and plastic surgeons and dentist and along with, and also with the patient, and he can give the different techniques for the assessment of the speech disorders, and he can diagnose the different speech disorders, and also for the therapy, that means how we can improve the speech. So that is also given by this speech language pathologist. Say clinically, like how they are going to evaluate. Say they use some X-ray or MRI machine to understand the internal speech production system, and also perceptual evaluation. Say like normally we can't able to judge what is the problem in the speech production system, but by hearing the speech sound itself, these expert clinical language pathologists, they can able to diagnose the presence or absence of any particular speech disorder. And there are some instruments are there like nasometry, then electroglottography. Using these also we can able to detect the presence of speech disorder. Say why this speech is so important, because every time we can't able to go and do the MRI scanning or X-ray scanning. Say just by perception of the speech itself we can able to diagnose whether the person is having some speech disorder or not. And also while doing the speech therapy or treatment session, we can able to easily say whether the speech is improving or not. If suppose if the speech is improving, then the person is like he's getting some treatment, and his internal speech production system or organs also recovering from the underlying like any disorder. So these are the different information we can easily get it from the speech signal. Say generally, just now I explained that in clinically, like different diagnostic tools are used for the evaluation of the pathological speech signal, but there are some inherent limitations are there. One is, as I said, no, we need to have some speech language pathologists, but availability of expert or trained SLPs is very less in some developing countries. And also there are a lot of variations are there. Say since the most of the time the person needs to listen the speech signal and he need to judge the type of disorder, but what happens is different persons will come with different opinion. That's what we can say that like inter-rater and intra-rater reliability is less in case of these conventional approaches. And one more thing is like it takes lot of patience and time of a speech language pathologist to come up with a good assessment technique or the good impression about the speech disorder. Say especially in our country, we have very less such speech sound evaluation clinics are available. So suppose these are different places where the some central government sponsored clinics are there. Say imagine our population. For this population, these kind of centers are very less. So due to this, the person will suffers like time and travel cost. So suppose if a person is having speech sound disorder, it will take lot of time to go for the particular clinic and get evaluated. So these are the different conventional like difficulties arise in the evaluation of the speech sound disorder. Say as a speech technologist, what we can do as for a solution, we all know that using speech signal we can extract some acoustic parameters, and using them we can able to develop some machine learning model or some system for the automatic evaluation of the speech sound disorders. So this may help an speech language pathologist, like he can easily use it as a supplement tool for the decision making. Then it saves lot of time for them. And one more thing is patient can use for the self-assessment, and also it can be used with some gaming or interactive GUIs, so it can be like more interesting for children with different speech sound disorders. Say how we can get some different acoustic cues from the speech signal. Say suppose this is a speech signal who has the normal and cyst means this is this disorder. They have some lump formed on the vocal cord. Just if you see the spectrogram of the speech signal, spectrogram contains some high frequency energy in case of this cyst disorder, because when we have like some disturbance in our vocal fold system, it will cause some kind of noise. So noise is generally like categorized as the high frequency sound. So that's why we can easily check with the some high frequency energy. Say, and also we can imagine that there is some periodically vibrating vocal folds are there, but due to this mass formation, that periodicity property will be lose out. So due to that, we can see that the pitch period extracted. So this is the pitch period extracted for the normal speech, and this is for the person with some vocal fold cyst. We can see that when we take the first order difference here, the difference is that for the this person with the vocal fold cyst. Whereas and also one more property, that is shimmer. That means just like the amplitude of vocal fold vibration, that also get varies for a person with the vocal fold disorder. And the person with hearing impairment, he will do lot of like substitution, omission and distortion additions. That means for some target sound, he will substitute some different sound. So suppose gadi is a word, just he utter as like dadi. Instead of ga, he just uttered as the. So these sounds also we can able to easily identify from the speech signal. Say this is the sound gadi, and this is he substituted as dadi. Say when we look into the spectrogram, here we can see that for gadi we can notice some energy around the 2 kilohertz. Whereas for dadi, this 2 kilohertz concentrate energy is not there. Next is cleft lip and palate. In case of cleft lip and palate, the roof of our speech production system, that is palate, is completely damaged out. Due to that, the sounds like trills, just we can imagine producing some sound like ra, like when we produce this ra sound, just we rotate our tongue against our palate. So in these cases, for a healthy speaker, we can notice that some periodic vibrations are visible in the speech signal when they produce this ra trill sound. For a cleft lip and palate speaker, since the palate is not working properly, due to that we can't able to find this kind of vibrating pattern in the speech spectrogram. Say this is one more example. Say suppose since cleft lip and palate speakers won't have some proper palate, they also do lot of substitutions. They, instead of saying papa, they sometimes say it as like mama. So that also we can visible in the spectrogram. This is for the dysarthria. In case of dysarthria, since the our speech production system and the nervous system don't have some proper coordination, due to that rhythmically we can't able to produce some sound. So suppose this is a repetition of the sound like pataka 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 repetition. Say in case of normal, we can see that the pattern is like almost consistent, whereas for the dysarthric speaker, this pattern is completely like after some time they can't able to produce such rhythmic sounds. So next I will going to explain the one case study, that is hypernasality estimation in case of cleft lip and palate and the dysarthric speaker. So first in this case study means just I will explain the development of some machine learning model for the evaluation of this hypernasality. Just I will explain what is hypernasality. Hypernasality means perception, that is listening of more nasality or like some kind of muffleness in the speech signal. Nasality means we just imagine that instead of person speaking through his oral tract or through the lips, most of the sound got emitted through the nose. So that means the particular person's speech like perceived like a nasal in nature. That means we can just imagine that in layman language term, instead of we sometimes used to say, right, the person is speaking through nose, like nose, say speech is coming from nose. So these kind of terms are like we generally hear for these person with cleft lip and palate. And the main reason for the production of this hypernasal speech is explained here. Say there is an organ that is called as the soft palate. Say the front portion is a hard palate. When it goes near to our throat, it will become soft, and it is referred as the soft palate. So in this soft palate, when we breathe here, say this acts as some wall here. Whenever we breathe, then it opens our nose to our lungs, and the air will passes through the our nasal cavity or from the nose. So when we speak, most of the time it should be closed here. Say so. This is the normal way of the normal way working of the soft palate. But whenever a person with cleft lip and palate, just imagine that this is the roof of our speech production system. The break is not only present in the hard palate, that is in the front cavity. It also extends towards the soft palate also. So imagine an organ who which acts as some valve. Say it is completely damaged here. Due to that damaging, it can't able to close the nose from the our mouth. So generally, whenever we speak speech, the nose part, that is our nasal part, that should be separated from the our oral tract. Say except some sounds. Say suppose while producing the sounds like na, ma, and na, that is nasal sound. During those sound production only, this soft palate closes the oral tract and opens the nasal tract. But rest of the time, always this soft palate is like closes the nasal tract. So whenever this soft palate is not working properly, then acoustic energy will escape through the nose. So then we perceive some nasal quality speech. So the major cause for this nasal quality speech is, as I explained, cleft lip and palate. One more is the dysarthria. So in dysarthria, what happens is the nerve supply for the soft palate is not working properly due to improper neural signal. The soft palate function got soft palate function got deviated from the normal production. So one more thing is the tonsils. So suppose if you have some tonsils in the speech production path, that also affects the speech production quality. As I explained, like speech got nasal, and most of the time we will get lot of speech production or pronunciation errors. Overall, we get some reduced intelligibility. So how we can rate the hypernasality? So suppose if the person is having more nasal quality, then we can rate it as like very high rating. It is a 7-point rating scale. So this is the normal signal.
The supermarket chain shut down because of poor management. The supermarket chain shut down because of poor management. The supermarket chain shut down.
The first sound is corresponding to the normal, and second one is the hypernasal signal with the rating as 5. That means as the nasality increases, the rating scale, the rating point also increases. And so this is how our algorithm aims to map these acoustic features into these particular ratings. Say suppose this is some acoustic use we explained here. One for the normal, mild, and moderate to severe. Moderate to severe means the ratings who has like 7-point or 6-point. Mild means around 1 to 2-point rating. So suppose there are some acoustic features deviation we can see here. So for example, this is a sound E. In the healthy production, we can't see any kind of intermediate peak between the 1000 to 2000 hertz. We can see some clearest valley in case of healthy speech. Whereas for the mild and moderate, mild and severe cases, we can get some peak in the instead of in the range of 1000 to 2000 instead of the deepest valley. So like this, we can have some addition of some here and there peaks and presence of some valleys in the speech signal. So these clearly indicate that using speech spectrum, we can easily capture the presence of abnormality in the speech signal. Say just we can use these acoustic features only for the detection of this hypernasality, but the problem is these acoustic cues vary along with the age as well as the gender and also along with the language. So due to that, we can motivate to go for the machine learning approach. Say they generalize these acoustic cues and give some reasonable or very like prominent results. Say how a machine learning algorithm can be developed. Say this is some conventional approach where we have the speech signal and we can extract some of the features like LPCC, RML frequency capsule coefficient, and we have the perceptual ground truth also. In all this clinical speech processing, the labels like whether it is normal or hypernasal are different categories like normal, mild, moderate, and severe. These labels are obtained from the expert clinicians itself. So just our machine learning model needs to map between them, and we can able to classify whether it is normal or hypernasal, or whether it is different severity grades we can able to get. But the problem is to develop such system, you need to have lot of databases for different categories. So suppose if you want to do some severity level classification for normal, mild, and moderate and severe, we need to have lot of data. So that is like a very practical problem in this clinical speech development system. So that's why as an alternative, just as a case study, we developed the 3 different systems where the first system uses some of the clinical data to develop the machine learning model, but rest of the 2 they won't require that much label data for the development of the machine learning system. So first I will explain this posterior based system. The major motivation for this system is the automatic detection of nasality by using the some equipment that is called as the nasometer. So in nasometer, what happens is just we have these two microphones which can capture the acoustic energy from nose and mouth. Just once we calculate the acoustic energy of mouth emitted from nose and mouth, just we compute some ratio, that is nasal energy divided by oral plus nasal energy. So this percentage will give us the nasal score. Say instead of nasometer, we can just equated the equation into two different posterior probability values. Say in case of nasal lens value, just that it is a ratio of nasal energy divided by oral plus nasal energy. Like that, if you have some posterior probabilities, say suppose we have two different models, one model for the nasal and another model for the oral, and from these models, just we calculate the posterior probabilities, and just we take the ratio between the these posterior probabilities. Say suppose posterior probability of the nasal sound divided by posterior probability of the oral sound again plus the nasal sound. All these are equated to the original nasal lens equation. And also if you have the DNN posteriors, these are the softmax posterior probability values. And using this probability value also, we can able to get the similar kind of some nasal lens score. For this, we can we need to have two models, one model for the nasal and one model for the oral. To develop such model, we just get the some speech sound, one speech sound from the completely like normal speech, normal persons, that is the oral sound. So oral model is developed from the oral sounds of the normal person, whereas nasal model is developed from the where we have the highest nasal lens score here. Say these are the nasal lens scores computed from the nasometry. The severe person, that is severe hypernasal person, for the nasal sentences. Say nasal sentence means the sentence like this, like Manu Anenu Nodida. That means most of the letters are the nasal letters. Oral sounds are the most of the letters are the oral letters. Suppose all the sounds are produced through oral cavity, whereas in nasal case most of the sounds are produced through the nose. So when we have two different data here, one data corresponding to the normal, that is computed from the oral sentences. Another model, that is nasal model, that is computed from the nasal sentence of this moderate to severe hypernasal speakers. So once we have the data, then we developed the a binary classifier. One model, say the binary classifier just classifies the nasal and oral data. Say the posterior probability computed for the nasal model, that is almost correlated with the clinical levels of hypernasality. Say in a pre-processing stage, we just passed our speech signal through the voice activity detection. Further, we extracted the MFCC features, and further using the data of the oral sentences and nasal sentences, just we developed the two-class classifier like this. Then using the posterior probability values, we just evaluated the hypernasality. So in case of GMM, it is straightforward. Just we have the one model for the oral class and another model for the nasal class. Then we computed the posterior probability for the nasal class. In case of DNN also, just we computed the posterior probability by using softmax equation, and using this we can detected the hypernasality. So these are the posterior probability values we displayed here. For the normal case, we can see that since there is no nasal acoustic energy emitted in the speech signal, the posterior probability values are very low for the normal case. So just I shown the motivation for using this glottal activity detection or the voice activity detection. It just says that whenever there is no speech activity is there, then we get some spurious spurious scores. So to avoid them, we just used this glottal activity detection. Say within the glottal activity detected region, just we computed all these frame level scores and we just averaged here. Once it comes for the moderate to severe region, it is clearly discriminable such that the normal speech has the lowest score, whereas the moderate to severe cases are having the very highest score in score. Say the database used for this work is say all the data is collected in a Kannada language, that is South Indian language, and there are like after perceptual evaluation, that is the clinicians are categorized the data into normal, mild, and moderate and severe. For a comparison, we just used the clinical instrument, that is nasometer. So these are the different scores we got. The model's posterior probability scores. Just I kept in the form of box plot here. Similar to nasometric scores, our model scores also like almost varies with the normal, mild, and moderate conditions. Whenever there is a moderate hypernasality is there, just it shows the higher value, higher scores. One for an evaluation, we made like two different like metrics. One is the correlation, just the correlation coefficient between these ratings and also these posterior scores. One more is the just like classification, that is whether it is normal or hypernasal. Hypernasal means it may be mild or it may be moderate or severe. Say this binary classification performance we just evaluated in terms of sensitivity, specificity, then accuracy. Say the DNN model along with the glottal activity detection, that shows the highest correlation with the perceptual label. And one more thing is these number when we develop a model with the deep neural network, that performance is far better than the conventional nasometer. Say one advantage we can see that to use the nasometer, we need to have some clinician or an expert person to handle that equipment. Like normal persons can't able to use the nasometer, but the speech-based system can be ported in terms of mobile application or any kind of portable device. Say that can be used by any persons for the evaluation of the hypernasality. So this is one highlight we can notice here. Okay, next approach we developed by using the healthy speech samples. In the last system, we have the oral and nasal models, where the nasal samples are taken from the hypernasal speaker. But next, for to develop such system, we need to get some hypernasal speakers. But getting some hypernasal speaker is itself a challenge in practical scenario. That's why we thought that why can't we use some large publicly available databases to develop some hypernasality evaluation system. Because like hypernasal speakers, as a normal speaker, we also produce some nasal sounds. So suppose this is a sentence here. So we have the different phonemes present in this waveforms are annotated here. Like nasal, we have the different sounds like N is produced by the normal speaker, N, then M and NG. So these are the three different sounds which can be produced by the normal speaker. Just we thought that we can develop some 4-class classifier like nasal consonant, nasalized vowel, say vowel adjacent to the nasal consonant that also have some nasal properties. So nasal consonant, nasal vowel, oral consonant, then oral vowel. So like this we made some 4 different classes and we trained some 4-class deep neural network classification system. So you can see that to train this deep neural network, we used only healthy speech database, because training the deep neural network requires lot of data, and practically getting this clinical data along with the clinical expert labels is difficult. So first we computed the force alignment, that means just we get the phoneme boundaries, and using these phonetic boundaries just we train the deep neural network for the classification of nasal consonant, oral consonant, and nasalized vowel and oral vowel. Further, this pre-trained model is used for the nasality score computation. Say further, once we have the nasality scores, we used some simple linear regression model to predict the hypernasality scores. So this model is referred as the model transfer approach because we have some pre-trained model. That model is applied for the hypernasality evaluation. That's why this approach is called as the model transfer approach. So this is the performance of the 4-class classification system. Say we used the 100 hours of Libri speech data, and Libri test is used to get these numbers. Say again we plotted the posterior probability values. So this is the data of the speaker with dysarthria. Like cleft lip and palate, we have the hypernasality in dysarthria also. So that's why whenever the posterior probability for the nasal consonant is high for the hypernasal speech, and whereas it is low for the normal case. And one more thing is posterior probability for nasalized vowel is less for the healthy speech, and it is high for the hypernasal speech. So once we have the phonetic boundaries, just we computed the nasal consonant probability for the consonants. So these are the different consonants we consider in this work, and the nasalized vowel probability for the different vowels. So finally we get the nasalization score. So it's simple, like whenever we have some utterance, just we segregated the scores for the nasal consonant and oral nasalized vowel. Just we averaged them across the frames. So finally we get the 17 phoneme level scores per speaker, because 17 phonemes we considered here. Whenever we come to the database, it has the 75 speakers. So this particular database is used for the hypernasality evaluation. So once we plotted the scores here, so these are the perceptual rating. Here we used the 7 point nasality rating scale, and nasality score computed for the consonant D. And when we plot these two, that means perceptual and our objective measure, they almost like linearly correlated. Here also the same thing we noticed for the vowel E. Say for the different different phonemes, we computed these nasality scores, and we noticed that some of the phonemes are highestly correlated with the perceptual rating. Some of them are very least. That's why we used some linear regression model. That means the scores are obtained from the model which is trained on the healthy speech, but to map them for the perceptual rating, we used the simple linear regression model. That means scores are derived from the healthy speech model, but to map them, we used the simple linear regression model. So first we computed the phoneme level nasality scores, and we just used the linear regression model along with the feature selection. These are the some predominant phonemes we got, like who has the strongest correlation with the hypernasality. So finally, when we map the perceptual rating and the predicted hypernasality score, say they give around 0.713 correlation with the perceptual ratings. So next is one more interesting challenge in this clinical speech is whenever we develop a model for a particular speech disorder, that may not be suitable for the evaluating other speech disorders. Say suppose hypernasality is a common phenomenon which is occurring in both cleft lip and palate as well as dysarthria. Initially, we developed a model for the dysarthric speech evaluation, but now we wanted to wanted to evaluate that for the cleft lip and palate. The linear regression model, which is trained on the posterior scores of the healthy speech model. So suppose linear regression model trained on the dysarthric speaker scores, say that gave like 0.689 correlation for the adult speakers with cleft lip and palate. Say the linear model is trained on the one disorder, but it can evaluate the hypernasality in different disorder. Let's say suppose the disorder is here, cleft lip and palate, and similarly it gave like 0.651 correlation for the children with cleft lip and palate. So we didn't fine tune any of our neural network or the linear regression model parameters. So this is not overfit for a particular speech disorder. So this is one requirement currently clinicians are expecting. That means a system trained for one particular disorder, they expect that should work for the different speech disorders also. Say one more work we developed, that is attention based work for this hypernasality evaluation. Say why this attention is required is say suppose most of the time our ratings are at the utterance level or at the speaker level. Say if the ratings are at the speaker level, then we just resample them for the different utterances. Say again from the different utterances, if we are extracting the frame level feature, then we assign those labels to each and every frame. So we can say that this is an utterance, say, and we have the utterance level label in our hand, but our features are at the frame level, but we need to assign them to each and every frame in the speech signal. But we know that most of the time what happens is these acoustic cues, not every frame level acoustic cues carries the pathological information. Very few frames carries the pathological condition of the speech signal. Say that's why we can see that we can develop some alternative approach, say to process this kind of difficulty in the data. That means finally what we do is we just extract the frame level feature, and each frame level feature is trained by using the utterance level label, and finally each and every frame level scores are averaged to get the sentence or utterance level score. So this is the conventional work happening in the clinical speech research. To avoid this, we just used some attention neural network, where by using attention neural network we can highlight some of the speech frames which are like responsible for the evaluation of the hypernasality. So this is the BLSTM based attention system for the evaluation of hypernasality. So this directly maps between the frame level feature to the utterance level nasality scores. But in conventional approach, what happens is these utterance level scores are assigned to each and every frame level feature, and finally these frame level scores are getting averaged to get the final utterance level score. But here it is a direct map between the frame level feature to the utterance level rating. So this is the architecture and mathematics behind the this utterance level network. Say utterance level attention based BLSTM model. So here we used the regressor because our scores are continuous in nature. So suppose why this is continuous is because we have the ratings from 4 or 5 different clinicians. Finally we get they get averaged out. So after averaging, the scores are in like continuous range. So they have some floating point values also. Due to that, we used the regression model here. So this is the weighted attention model. That means just each and every state of this BLSTM model get weighted and they get averaged here. So this is the speech database, and here also we used the different database, that is AmeriCleft speech database. It has the 60 children with cleft palate and 10 controls are there, and it is an one-to-one mapping here. That means the model itself trained on the labels of the clinicians, and since we have the 5 different raters and we just calculated the inter-rater correlation, that means from one rater to another rater how much correlation is there, that should come like very good value. We are getting very good correlation here. Say one more thing is, since we are training the deep learning model, we need to have some data augmentation, because originally the sample size is very small. That means we have very small database. For that we did some like data augmentation. For each sample we just did the 26 copies of the speech signal by using the like noise augmentation, then the utterance level, then word level speed perturbation, and vocal tract length perturbations. And one more thing is, since we have the like for each severity category, say suppose normally we have more data, and for this severe case we have like very less children. For the less cases we did more augmentation. For the more available data we did less augmentation. So like that we did some balancing here. So this is the like speakers, and along with the number of sentences available for the each of the severity category. Say suppose for severe cases we have only 48 sentences in the original data, But after augmentation, we got like more number of samples here. So once we trained the model by using our augmented data against with the expert labels, then I plotted the attention weights here. So we can see that the attention weights are like highly giving some weightage to the oval regions. Say E and E for these regions. The word is here sissisa. In case of this E and E region, we are getting the very high attention weights. This says that the voiced portions are like highly responsible for the perception of hypernasality. So this is true from the clinical section, that is from perceptual or listening experiments, and our deep neural network model also gave the like highest weights at the for the vowels or voiced regions. Further, we evaluated like for different severity cases like normal, borderline, mild, moderate, and severe cases. We just evaluated the attention weights here. So just I will explain here. For the normal case, like high vowel means this E and I. These are the high vowels. These are showing like very highest significance for detecting this hypernasality. Whereas in case of borderline and mild samples, only high vowels are more significant. But in case once it comes for the moderate case, this low vowel also contributing somewhat in the detecting hypernasality. Once it comes for the severity, the attention weights of the attention weights for the all the voiced consonants like low vowel and the semi vowels and the voiced stop, all are showing the like very highest attention weights. So this shows that the hypernasality information like it varies along with the severity. So suppose most of very like in very mild cases only high vowels are significant for detecting hypernasality, whereas all different voiced consonants are responsible in case of severe hypernasality. And all the unvoiced consonants are not at all contribute any information for the hypernasality detection. So this is the final scores we got. Say as I told that since we averaged across the 5 different raters, the perceptual ratings are in continuous range, continuous number in range, and also this predicted scores also we plotted along with the x-axis. Highest correlation we got like 0.684, and as a comparison we did like BLSTM attention, then for feed forward DNN. Here it is the conventional approach, frame level assignment to the each of the MFCC feature vector, and finally we averaged at for each utterance level. Then the BLSTM frame level, here also BLSTM for BLSTM network, the labels are given at the each and every frame. Here the BLSTM final frame, that means only final frame is assigned with the utterance level label. BLSTM mean pooling, here for each utterance we just did the average across the outcome of the different frame level BLSTM states. So each say suppose each frame level BLSTM state is got averaged here. So that is the BLSTM mean pooling. When compared to the our attention model, BLSTM mean pooling is the little bit comparable. But however, we are using the attention weight to average the BLSTM outcomes. So that's why this attention model is giving the better performance. So these are the correlation coefficient, that is Pearson correlation coefficient. And another metric we used the this mean absolute error. That means what is the difference between the absolute difference between the predicted scores and the perceptual ratings. Say, so this is a case study we did. We just developed, I just explained the 3 different systems. One purely by using the posterior probabilities. Next by using the model transfer approach. That means using healthy speech samples, how we can evaluate the clinical speech. The third one is by using attention network, because most of the time the labels are at the utterance level. However, our features are at frame level. How we can map between both of them? So by using attention model, we just solve this issue. When coming to like clinical speech research, There are a lot of practical issues we need to consider. Mm, Say one is the what is the clinical requirement clinicians are expecting. Say suppose if we develop a clinical speech processing system, ultimately the speech pathologists are the this paramedical team, or the patients are the end users for this system. For them, how we need to develop the how we need to design the system. So that is one thing. Another thing is like stimulus preparation. Just I will explain later what is stimulus. Mm, how we need to do the data preparation, and what are the appropriate features we need to use, and what are the labels we are going to get. So final thing is the user interface development. Say suppose in case of clinical requirements, these are the 5 different area to work in this clinical speech processing. One is we can easily detect the hyper articulation errors, say that in pronunciation errors. Hypernasality is the presence of nasal cues in the speech signal. The intelligibility, then voice quality, then cognitive impairment. So these are the 5 major areas currently clinicians are expecting us to work. For example, for articulation assessment, we need to have some target sound. That means the stimuli means here the target sound. Say suppose for a person with pronunciation disorder, we just ask them to produce this word gadi, then he may produce it as like dadi or kadi, anything, okay, what else with some pronunciation error. So development of these particular words is an important step. Say what is the target consonant we need to have, and it should be embedded in the different 3 positions. Say suppose initial, now ga is in initial position, then the medial position, and at the final position. Like that, we need to develop different words for the articulation or pronunciation assessment. Further, we need to develop some sentences which contain the target consonant. In terms of rating, for articulation, we have the soda error rating, that is substitution, omission, distortion, and addition rating. Then also there are some categories are there, whether the sound is backing, or that means the sound is substituted by front sound or back sound or glottalization. And the easiest approach is the severity on a rating scale. So if the person is having pronunciation disorder, then how much it is severe. Say suppose it is whether it is on the equal appearance scale, that is 0, 1, 2, 3, or it may be some visual analog scale, that means 0 to 100, any continuous score we can also write. So these are about the articulation disorder. Next, for the voice disorder. For voice disorder, we need to have some sustained phonation like a, e, u. That means the voice disorders are related to the vocal fold. We need to have some sounds which can reflect the vocal pathology. And here also ratings are like sample level voice quality rating and speaker level voice quality rating. Sample level means for each utterance, the clinician will rate the what is the severity of the voice quality. Speaker level means we have n number of different samples. That means sample of a, e, u, and some sentences. By combining them, they will judge a specific rating for the speaker. Next is some instruments are also available. Like for hypernasality, we have the nasometer. Here, like stroboscopy, where we can directly visualize the vocal fold. So that is one issue, or one kind of ground truth we can consider. And the task is here, like clinicians are expecting us to not only differentiate between the normal and vocal fold disorder, they also expect us to provide some hints about the presence of different pathological condition, whether the cyst is present, nodule is present, or polyp is present. So this is one expectation clinicians are expecting from engineering team. Hypernasality, I explained like 3 different approaches currently. For hypernasality measurement, the stimuli are like we need to we need to ask the person to produce some phonation, or the sentences contain the oral consonant. Just for a curiosity, just the explanation is, for articulation production, the sustained phonations are not required. That means for pronunciation, we need to have the words rich with the some consonants like that. For vocal disorders or voice disorder, we need to have some samples with the vowels or sustained phonation. So this clearly says that the samples are the data we are going to collect from the disordered person. That specifically depends on the clinical requirement and on the speech disorder, the type of speech disorder we wanted to evaluate. Next is the once we have the data prepared and also some clinicians are evaluated them, then the next step is the ground truth validation. So suppose as I said that this perceptual ratings are the ratings given by the expert speech language pathologist. They are the ground truth to develop the machine learning model. Say in any kind of machine learning model, if ground truth fails, then our model trained parameters and model fails to do its actual task. So that's why we need to take lot of care while preparing this database and this ground truth. Say that's why we need to collect, we need to take the rating from multiple raters and just we need to find some correlation. So suppose say inter-rater reliability, that means correlation between the each pair of the rater, and intra-rater reliability, that means to say actually what happens is whenever we gave to some samples for the evaluation, at first time a same rater rate one category of ratings, next time his rating may change, so that's we referred as the like intra-rater reliability. So to evaluate them, just like 30% of the previous the first time speech samples are given at the second time. Next we need to calculate the correlation between the first time and second time sessions. So this session variability we can compute, and also we need to maintain like same environment and same headset for all of the rater, because sound quality get vary along with the headphones and along with the environment. So when coming to the AmeriClef database, that is Cleft Palate speech database, we got like rater 1 to rater 2 correlation as 0.72, rater 3 to rater 4 as 0.7. So this is almost reliable things. That means different raters are rated our database with the same correlation value. So that means at least around 0.7 correlation we need to get as an inter-rater reliability score. So then only the data we can use for the developing any machine learning model. Say how the stimuli is prepared here. That means we can present the stimuli in terms of audio. Say suppose the person is like a very elder person, then we can just provide some text or audio information. Whereas if we are dealing with some children, then we need to produce some images to produce this particular sound. So different ways are there, one text, audio, as well as the picture. The next immediate step is the once we have the data and along with the ratings, the next step is the segmentation. That means when we do the recording, we get lot of like what do you call background noise and unwanted like the speech of the instructor. So we need to remove them. So one approach is like we can use some tools like Pratt kind of thing. And one more thing is like if you wanted to analyze at different phonemes, we need to have, so suppose I want to analyze only the phoneme ma or na, then this force alignment is a technique which can provide us the phonetic boundary. Say there are two tools are there. One is this Montreal aligner. Another thing is we can use directly our Calvi model to or any ASR model to get this force alignment. But available model is Montreal aligner here. Just we need to have the acoustic models or the ASR models to get these phonetic boundaries. So these are the like Montreal align based scripts are there. Most of the time our like this clinical speech analysis is the at phoneme level. That means say suppose if you are analyzing the vocal disorders or voice disorder, then we need to segment out the vowel regions. That means a, e, u, these kind of vowel regions. To do that segmentation, we can directly use this pre-trained Montreal force aligner models. One more approach is the landmark-based approach. That means using some energy-based cues or acoustic phonetic cues, we can segment out the speech samples. So speech mark is one such toolkit where we can by using this acoustic cues like energy-based cue, we can able to get the phonetic boundaries. So the advantage of this model is to get the force alignment, we need to have a ASR system, that is automatic speech recognition system. To train that ASR, we need to have a lot of data. So for if you have like very less data in any like very limited resource languages, then we can easily use the this energy based approach or this speech mark tool. So this is the segmented sound here. So we need to segment the sound different phonemes here. So it is easily segmented. The red color one corresponding to the segmented regions here. So here we wanted to segment some fricatives. The red color cube gives the fricative cues. So we can able to get the fricative boundary by using this speech mark bound. One more thing is like there in Prath we have Prath is a software where we can do this voice analysis. That means what is the pitch and how our vocal quality is present. Say for this vocal quality assessment, there is a Prath information is there. That is the voice report is available in the Prath software. Using that we can assess the our voice quality. Then coming to the feature, once we have the segmented phonemes, then for the feature we can use either Prath or there is some OpenSmell toolkit is there. Using this OpenSmell tool, we may get around 1000-dimensional speech features. So using them also we can process, like it will give the harmonic to noise ratio or fundamental frequency. Different acoustic features we can get from the OpenSmell tool, and lot of researchers are using this OpenSmell tool to develop some clinical speech processing system. When coming to the classification, once we that means we have the data and we have extracted some acoustic features, and now the final goal is to develop the classification. Say in the classification, we need to have like the model need to train on the acoustic features along with the ground truth ratings. The ratings might be at speaker level or at the sample level, but our features are at the frame level. Hence, there is no one-to-one mapping is occurring here. The common way is to assign this sample level rating to the frame level features and do training our model. So that is one approach. That's why to overcome this approach, we just used the attention based model. Further, like we can compute the various statistics of the frame level features like mean variance to convert them into the frame level features to the utterance level. Further, we can use the train a classifier against utterance level labels. So one thing is like assigning this utterance level to each and every frame and train the machine learning model. But another way is to just average out or get some statistics of all of the frames and train those features for this utterance level labels. So that is one more way of mapping is existing. Finally, like if you have like frame level features are trained, final score is getting by the just by average out of the classifier score. So there are two approaches are there. One is just by assigning utterance level scores to the frame level feature and train the machine learning model. Another one is we have only the utterance level label, just compute some statistics across each of the frame, like mean and variations of the different frame level features, and training machine learning model by using those utterance level features to utterance level labels. So that is one more approach we can use. Say once it comes for the deep learning model, we need to have lot of database. Say practically in clinical speech, we won't get such high amount of database to train our deep learning model. Say there are two approaches are there. One is transfer learning or model transfer approaches. That means model is trained on the healthy speech data that is largely publicly available healthy speech databases, and use them for the use some fine-tuning techniques to adapt them for the clinical speech. Another one is the data augmentation. So both models I just explained for the hypernasality case study. Data augmentation also, it should be very specific to the particular speech disorder. Say noise addition may not be suitable for the breathy words or the some vocal quality evaluation, because this pathological speech or the clinical speech also contains some inherent noise. Hence, the addition of some babble or white noise may actually like interrupts or the it may not be suitable for the this particular task here. And different techniques like pitch perturbation, speed perturbation, vocal tract length perturbation, different techniques can be used, but the condition is we need to check whether the addition or the data augmentation technique should not affect the acoustic use of the pathology or the clinical condition. Say addition of noise will affect the actual clinical cues of the breathy voice. So that's why we should not use the noise addition for the breathy voice or the vocal fold pathological evaluation. And actually there are different packages are available. Say in Librosa we have time split and pitch shift techniques are available. We can use them also for getting this data augmentation. One more thing is like pre-trained models we can use. Say suppose in case of like pathological data, we use the pre-trained model and the large healthy speech corpora. Then the choice of pre-trained model also like depends on the particular task. So suppose for hypernasality, I just show that I used the train classifier, which is trained on nasal and non-nasal sound classification. For intelligibility system, we can use the deep learning posterior probabilities. Say there is some common tool is there, goodness of pronunciation, which are used by the like ASR posterior probabilities, where the ASR is trained on the healthy speech corpus. So that is one more model transfer approach. And one more thing is directly we can fine tune our pre-trained model. Like last few layers, we can first few layers we can freeze it, and last layers we can adapt for the clinical databases. As a summary, just like in case of this pathological speech evaluation, just I explained the different cases of clinical speech conditions and its like physiological or the anatomical defects. And one more thing is like as a case study, I showed the different posterior probability based approaches. One is like posterior from the clean speech and posterior from the healthy adult speech. So that is one model I explained. One more thing is the model transfer approach, and one more model is the attention based approach. So three different case studies I explained here. In future or for the future research, we can use the currently like deep learning is making a lot of progress in speech research. So that's why we can use some pre-computed embeddings or the outcome of the some intermediate layers to get the clinical speech evaluation. Whereas to get these embeddings, we can use the healthy speech model, and these embeddings can be used for the clinical speech evaluation. Next is one more important thing we need to consider, it is an research here. That means model should not overfit for a particular database and rating. So suppose if you want to evaluate the voice disorder in dysarthria and in some suppose in some vocal fold disorders, in both vocal fold disorder and dysarthria, this voice quality evaluation is an important thing. But the model should not like overfit to a particular disorder. Say that it should be more generic towards the both disorder. Then it is easily acceptable by clinicians or any other person or any paramedical team to handle it. That means they are also get fed up. Say suppose if we develop some system for a dysarthria, and again if we develop some system for a vocal fold disorder, they will get confused which system we need to use to evaluate this voice quality. So those things we need to take care of. And one more thing is like if you train some DNN system, that should be not that much dependent on the rating scale. So suppose some clinicians prefer to use 4-point rating scale, some prefer like 5-point, some prefers to use some continuous rating scale. Somehow we need to overcome with the rating scale dependency. One important research thing we need to consider is the acoustic features are the model, whatever we develop for this clinical speech system, they should not interact with the other disorders. So suppose we just wanted to develop the hypernasality predictor system. Along with the hypernasality, there are some prosodical errors and pronunciation errors also exist. So our developed system should only focus on the hypernasality cues, and it should ignore the prosody and articulation disorders. So this is one more thing we need to consider while doing this clinical speech research. So thank you, and any questions are there?
Hello.
Hello.
1 second. I'll just.
Okay.
Yeah. Hello. If I'm audible.
Yeah, I'm audible.
Thank you. First of all, thank you so much, Vikram sir, for this in-depth session on speech disorders and how, like using different ML techniques, we can assess and evaluate these disorders to help the clinicians. So we have a few questions which we have received on the form that we rolled out for questions. So if it's fine with you, I'll just ask them here.
Okay, yeah, thank you. I will do.
Okay. So the first question, first question is that what would be the best advice for a final year BTech student who is interested in speech processing and machine learning research? I want to know about the scope.
It is a generic question or generic in different domains of speech or only for clinical speech? I think it is general, right?
Yeah, I think they mentioned speech processing, but you can also go into clinical speech in specific if you want.
Okay, for final year BTech students, I suppose development of ASR may require a lot of resources. I suppose if they wanted to use some deep learning technique, again, the facilities are also matters here. So that's why they can start with some simple classification techniques like emotion classification, like happy, anger, or sadness classification. If they have some good databases available for this clinical research, just classification between the normal and different speech disorders. Say that is one more approach. Say just they can start with some simple linear regression model or the support vector regressors to develop their system. And if they have some proper facilities, they can go for the deep learning techniques.
Got it. Thank you, sir. And we have a few more questions which are like general questions, so I'll ask them. The second one is, how was the experience of doing a PhD? No, how the experience of doing a PhD from India and postdoc from USA compare on environment, people / students around in a few words? Like they want to know the comparison between PhD in India and postdoc from USA.
It's difficult. Like both way I learned a lot of things. That means in India, what happens is like both are having some pros and cons. That means to say, in India, like more we are oriented towards the result, and we need to we are more strict each other. So suppose in India PhD happens like this, we need to have some proper topic, and all our work should be focused on a particular topic, and we need to write some thesis. But in US, what happens is they choose a lot of generic topic, and they do around 3-4. They just explore the 3-4 areas in that broad topic, and they publish their thesis. So in kind of flexibility, US has a lot of flexibility. But here, whatever we choose, we should focus on a particular thing. But moreover, one more thing we can notice is in India, it's depending on a person's perspective. Like say, suppose if you want to in India, the focusing is more. That means we go more depth and depth. But in US, not like that. It is like it is a broad topic. So whatever you can do, just you get some good results or some contribution, you can write your thesis. So both way, like when something has like advantages and disadvantages. So suppose in India, what happens is we focus on a particular topic, but if we don't get any particular result, we need to struggle there. But there it is not a case. If you don't get result, just change that area, and you can work for 3-4 different areas and publish your thesis. So like, okay.
Right, got it, sir. So I think the next question is also a little bit on a similar track. It's just that they're saying if the students are looking for a master's degree this time in related field, as in speech processing or in any AI/ML, so is it better to go for top IITs or US is a better option?
Okay. No, both are almost same. Like I didn't find when compared to IITs and US universities, I didn't find much differences. Okay, not both were like quality wise, both are almost equal. I didn't find much differences.
Yes, sir. Well, okay, but it's I think that was a similar question, and then next we have. So yeah, next question is also along the similar lines that if you know what are the universities in India and in USA performing state of the art research, I think that maybe we can take it for like speech related research.
Okay. Okay, state of the art means say it depends on the area. Say the university where I worked in, that Arizona State University, say they're more in that in that team the lot of focus is happening on the clinical speech research. But other universities, like if you consider in Stanford or MIT, there I found little bit less work is going. So again, when it comes to the in India, currently on this clinical speech processing, IISc is working, and in IIT Guwahati, we just like 4 of us started this work, and we did some progress. But when it comes to the generic topics, like it may be like automatic speech recognition and speaker verification, the good universities like CMU or Stanford, they are working like better way. In India, like state of the art work is going at the like major work is going at IISc and as well as IIT Madras about ASR. Yeah, it's completely like depending on the team and area and the professor's interest also. So different universities have benchmark for the different work. So suppose if you come for the Prosodic verification and Prosodical model, the like emotion recognition, IIT Kharagpur is good. Like they have more work. So it's completely depending on the university. Not like in one university we get all of the different progress or different work.
Sure. So okay. So like different universities have different like areas where they're really specialized in.
Correct.
Okay.
Yeah.
Okay.
Like different engineering teams in speech research also, we have like different teams are working in different universities.
Got it, sir. And so we have another question from the forums, which is related to clinical speech. They're asking, what is the scope of getting a clinical speech data available for researchers? So the scope of speech data, clinical speech data.
There are like very less databases available. One is the Targo database. So we can that is a more commonly using database, and dysarthria. On vocal and cleft palate, we don't have much publicly available database. But on dysarthria and on this Parkinson disease, we have a lot of databases are available. But all are in American English. But if they wanted to, if we want to do research on the Indian languages, we don't have not that much standardized database. For that, we need to develop our own in-house databases, and we need to work. And in most of the case, what happens is in clinical research, they always collaborated with some clinics or with the doctors. So just along with the collaboration, they develop some database, and by taking them, they will work. So in most of the time, in-house databases are the like good solution to do research in this clinical speech research.
Okay, sir. So I hope that answers the question, whoever asked the question. And next we have a question from our YouTube chat. This is being asked by Parishmita Gogoi, and the question is interesting. First of all, she's complimenting you, sir, and she's saying, "Ma'am is saying interesting topic and nice presentation." Next, the question is how prosodic cues are deviated in the pathological speech.
Okay. In pathological speech, especially in neurological disorder, the prosodic cues they get affected. So suppose prosody is a major aspect where we can observe the prosodical cues at around 100 to 150 millisecond cues. They are not at frame level; they are at segmental, suprasegmental features. They can be extracted from the 200 or very large segment of the speech signal. The neurological coordination between the our speech production system, that means our speech production organs and our brain system, both are affected in case of the neurological speech disorders. So due to that, prosodical information get varies. So suppose something like repeated chantings, some repeated sound repetition. They have rhythm. They have like highly rhythmic in case of normal. But once it comes for the neurological disorders, that rhythmicity will deviated from the healthy speech. So rhythm is the one important prosodical cue we can observe in the clinical speech samples. Rhythm and monotonicity, they can't vary prosodical cues as normal. Most of the time they produce like monotonic sound. So that is one more cue.
Okay, thank you, Sir Vikram sir. I hope that answers Parshudam's question. So yeah, with that, I think we are done with all the questions. And once again, thank you so much for the session, sir. And if Shishir sir, you want to say a few words, and
Okay.
I'll hand it to you.
Okay, yeah. So thank you, Oigan. Vikram, it was a nice talk, and you gave a brief overview of like how if one person wants to do some work in pathological speech and how they should start, and you gave a very great overview of that. So I have one question that will be the last question of this session. That is like these models are like whether these are language independent models or like what we need to do like if we want to make this pathological speech evaluation models language independent. For example, I build one model on Assamese, then whether you can use for Hindi or Kannada like that.
It depends on a problem specific. Say suppose if we are evaluating if we are developing a system for pronunciation error, that should be highly specific to a language. So that we can't able to do anything because different languages have different pronunciation cues and different phonemes. But when it comes to an voice disorder or this kind of generic sound like hypernasality or vocal fold quality evaluation system, so these systems we can try for a language independent system. Suppose we develop a vocal quality system evaluation system for a Assamese, then depending on, because the thing is the vocal quality evaluation system, it should not depend on a particular phoneme. So suppose a, e, u, these sounds are like independent of any of the languages. So if you develop some system at phoneme level or at the sustained phoneme level, that can be easily usable for the another Indian languages or English also. So like that it is possible. In clinics also, the systems developed by the Western countries, say suppose doctor speech or these kind of voice quality evaluation system, they are easily tuned and used in our Indian clinics. So it depends on the pathology. So on which pathology we wanted to develop.
Okay, thank you. Okay. So yeah, Abhigyan, I think you can conclude this.
Yeah, thank you for Assam AI initiative team for this opportunity. Yeah. Okay, thank you.
Thank you, sir, and thank you to all who have been watching this session. So yeah, we'll end the stream.
Thank you.